Okay, thanks, Richard. On this presentation, I'll try to go through it reasonably quickly. My main purpose of this is to give a broad overview of what shape models are about and some of the issues behind them, rather than go into the detail of how we use the shape modelling to get results out of occult. Now, why use shape models? The shape models provide the shape but not the size of an asteroid. And they do that by light curve inversions of photometric light curves that people take. The key thing here is that because the shape models show the irregular shape of an asteroid, and if you can fit a shape model to the occultation chords, irrespective of the orientation of that shape model or the asteroid, the occultation chords provide scale for the shape model. And this gives you a direct measure of the volume equivalent diameter to be measured, or it can be a surface equivalent diameter. The phrase the volume equivalent diameter allows you to talk about what is the diameter of a house brick, which is a sphere having the same volume as that brick. One of the other interesting things is if you've got a very well observed event with a good shape model, the nature of the shape model is the origin of it is the center of volume. And if you assume uniform density, which is a half reasonable assumption, then the fitting of the shape model to the chords actually enables you to locate the center of mass of the asteroid and not the center of figure. Now, this is particularly relevant in the context of astrometry and orbit determination, because the motion of the asteroid around the sun is governed by the location of center of mass, because its mass is the thing that drives things. Now, center of mass for optical astronomy, astrometry, never heard of in practical terms before what we've been doing. And there's an IOU standard for reporting astrometry, which was developed over the last few years. And because of our capabilities in this area, that standard has actually been updated to allow for our ability to measure center of mass of asteroids. Here is a sample page for a fit of an asteroid to some light curves, so some occultation chords. I'll just go quickly through what's plotted. Here's the shape models you can see, and our occultation chords. Overall, a very good fit. There's some differences down here. Down here are some scale lines. The top bit there specifies the mean diameter for a volume on a volume equivalent basis, and the bottom of that is the mean diameter on a surface equivalent diameter. Interestingly, the surface equivalent diameter is always greater than the volume equivalent diameter, and the satellite determinations of diameters are all surface volume equivalents. When we do a fit like this, down the bottom of the screen, you'll have this display here, and it gives you, when you fit the chords to the asteroid, it gives you a direct measurement here of the volume equivalent diameter and the surface equivalent diameter. And you can see that it differs by 6 kilometers. So that's the important bit to do. Up here, and I won't go into any detail of this, this is a form or panel that appears on the plots, which allows you to control the display and set various parameters, such as the fit quality and the diameters you derive from the measure. In this case, Dammit has 3 models. You can see them in dark there. Those ones grayed out. Under ice, and for this, it's got 6 models. So that's the basic appearance of the event plot with shape models displayed. The bit I won't go into is the process that Dave Galt and I go through, and some of the, I think John occasionally does it, or somebody in your thing, is you do the fit, and for each of the models, you set these parameters of what's the quality of the fit, and the 2 diameters, a minimum and maximum diameter. Anyway, moving on because we're short on time. Here's a nice fit, which shows how that's a really good shape model of Antiope, or however you pronounce that, which shows how our chords are much better than anything else. And you could actually, if you, with this one, you can look at multiple occultation events with Antiope. You can start working on changes to the orbital period of it from our occultations. One of the challenges with determining shape models, which you have people monitor the asteroid for many hours on one night to derive a rotational light curve. And you do that for the asteroid in different parts of its orbit and to derive the shape model. A first step in that process is to identify the orientation of its axis of rotation. Now, I don't understand the detail of how they do this, but almost always there's an ambiguity. There are 2 solutions for the orientation of the axis of rotation. And the models are vaguely similar, but can be materially different. Here's one asteroid, 2 shape models. On these shape models, the red axis is the North Pole, the blue axis is the South Pole. And you can see our occultation chords, and these chords can be fitted nicely to this model. And however you move the chords around on this model, you can't fit them to it. So the conclusion here is that that's the wrong model. This has got the correct polar axis, that one doesn't. Okay, next one. And just because you've got a shape model doesn't mean the shape model's right. This is a recent event in January this year. And the chords are quite interesting. You've got a broad chord here and a sharp arc there. And it's clear with the consistency between observers. This is not an observational anomaly. This is a real event, real nature. This properly reflects the shape of the asteroid. This asteroid shape model doesn't fit that at all. Whereas this one doesn't really fit it either. But maybe you could derive a minimum diameter from it, but very unreliable. So that both of those shape models are not right. One of the good things, particularly for astrometry, is dealing with shape models. You can see here we've got a bunch of chords. You can fit an ellipse around those chords, and you'll have the centre of the ellipse about there. Hey? Somebody's got their microphone on with and blowing their nose. But here you can fit it to the shape model, and there's the centre of the shape model. That's the centre of mass. We know where that is. So that's the astrometric position we report, not the center of all these chords or ellipse fitted to those chords. And then you can get, this is Eros, which is a bean-shaped asteroid. Here's one fit there, and surprisingly, given the shape of Eros, those chords are actually fairly uniquely placed on that asteroid. If you start moving them around, up or down or left and right, they go into misalignment quite quickly. And here's a different orientation of that asteroid. And if you fitted a circle around those chords, you'd be vaguely near the center of mass of Eros, but not really. This one there. I mean, just an illustration of how with elongate asteroids, shape models make a huge difference in determining where the asteroid is. Now, this is just summarizing what I've just said. When you're going through this, there's in here the version info given on that form there, which gives a bit of extra info if you might find it useful. If you've got a shape model, what information do you have readily available? Well, there's some tools in Occult. If I go back to the normal plots, this is how events, no point me pointing, this is how events normally come up, and that's on the screen that plots the event. But behind that, you'll have also somewhere on the computer screen the form which actually does all the hard work with drawing the shape model for the relevant date and time. On that form, there's this panel here with model image. If you go down here, there's the thing, list model parameters and light curve dates. And here you've got, for the 4 different models that are available for this asteroid, you've got the orientation of the pole, and they're in ecliptic coordinates, the longitude and latitude of the ecliptic. And the Dammit and ISM models are actually the same in this. And the rotational period, and those can vary. And this is effectively the ephemeris for it. Importantly, down here, you have the light curve dates. And here I need to make a particular point here. The light curves which are of greatest value are those which are made on specific dates, like these 3 here. In recent times in Dammit, they also have incorporated magnitude measurements from the Lowell sky surveys and Gaia. And I think there's another one there as well. And they're not precise as precise measurements, and they give a very approximate shape model at best. Generally better than nothing, but not much better than nothing. What you can see from this asteroid, we've got 3 dedicated light curves made over a period of 7 days and 43 years ago. So the observations are very limited over a time span and made a long time ago. And that tells me that any light curve, the light curves used for this model are not as many and good as one would like. And the shape model is probably not very reliable. Perhaps more of interest there is you can actually see the fit of the observations to the light curves predicted from the model. To do that on the shape model form with model image, display model fit to light curves. It's only available for DAMIT shape models, and you must have it's provided for the relevant shape model that you've got selected. So in this one, it's the fit is to DAMIT model 889, not 890, which is just off the screen there. Click that and you get a form which shows, here's the red line is the predicted light curve and the blue dots are the measured light curves. And you can see that the measured values don't fit entirely closely to the predicted curve. Got them over there. And you can see that that light curve is almost the same for all of them, which means the resolution is quite limited. And here is Lowell Observatory, and I forget what the difference of those two are. It's in the notes somewhere. You can see how the data there is scattered. It's a different type of plot, but lot of scatter. Using this plot, you can assess the reliability of the shape models from the number of dedicated light curves. So how many of these have you got? The more, the better. The time span covered by the light curves. So this is 7 days. Desirably, you have a time span measured in years, many years. You're looking for the number of different shaped light curves in these dedicated ones. They're all the same shape. You want to have different shaped light curves, and you'll see that in the next slide. And then the quality of the fits of those light curves. These are some of the light curves for Eros, which sort of illustrate this. That one is in 1953. This is from 1953 to 1976. You can see where you've got some high amplitude light curves here and very, very low amplitude light curve there. I've managed to duplicate that. And that's 31. And here's another one. This is 91. That's in 1976 as well. But you can see some light curves are very flat, intermediate variations and large variations. It's this change in variation of the light curve which is used to develop the shape model. And you can see here, and the observed points don't fit the predicted light model very well at all. Most of them do, but there's significant deviation from a number of them. And you'd expect that with all fits, but with Eros, you've got a large number of light curves, so you can start thinking maybe the data there is not quite so good, or there's some fine-tuning required of the shape model. But that's a very useful tool to look at to get a sense of how good is my shape model. When doing the fit to the chords, you can rotate the shape model on that same plot form. There's the model image thing. There's with phase models, you can draw the asteroid at a series of different angular orientations. When you select one of those, the part of the display panel on the form comes up with a series of buttons which gives you different phase orientations. So on this one, if I click -16, that gives that orientation of Eros. 0 is that orientation of Eros. And this last one is actually +16 degrees. So you can play around and see whether by adjusting the rotational orientation, you can get a better fit. For an asteroid like Eros, where the light curves and the duration of covered by the light curves is highly precise, you wouldn't normally want to change their rotational position. For the previous asteroid where the light curves are not many, and the main ones were 40 odd years ago, changing the rotational orientation may be well justified. Now, it's always useful to play around with some of these things to get a sense of what you can get out of shape models. So I'll just do a couple of demos. This is from, let me just, yep. On the ephemeris forms, there's a box there for shape models with a small one there for demonstration. And when you click that, you'll get this form where you can select the asteroids and have them displayed. Now this, I've got two asteroids in there, Ceres and Vesta, which have come out of a space mission. You can see lovely detail in Vesta. This is Vesta. And this form allows you to change the date, the time of what's displayed. You can change the background colours, whether it's as you see it in the sky or projected on the Earth. You can turn off the axes of rotation. And up here, you can also display a full rotation. And when you've got more than one model, you can select the model that you want to have displayed down there. Now, hopefully I need to, bear with me a moment while I bring up what I need to bring up, which is okay. Can you see, I hope you can see on the screen, Eros. Now, if you go through here, I'll just show the three different shape models. Oops. Well, that's a rotation of it. So you can see what it looks like. I'll turn the rotation off. So that's one shape model. That's a separate shape model, not much difference between those two. And this is a third shape model, which has a significantly different orientation. The surface looks different because this has got greater resolution in the calculation. Doesn't necessarily make it any better. It's just the mathematics they've done. I'll just show that's a black background. You can have a white background, or you can show blue. It takes your fancy. Changing between black and white facilitates what you do when you're plotting it against the your occultation chords. You can match the background to the occultation chord plot. That's how the asteroid looks in the sky. If you've got an occultation event and you're looking at the path on the Earth, you swap it to the Earth plane, and that's the shape of the shadow as projected onto the Earth. You can turn the axes on and off. Now, and as you saw before, you can do the rotation around there. Now, one of the nice things you can do there, this is for today. I'll go back a month to July. And you can see the different orientation of the asteroid. Go back a previous month. And go back previous month. And let's go back a year. This gives you a handle on what how the thing is rotating and how the orientation differs at different times of the year when you're looking at these things. And if I go back to today, if you watch closely with this, hopefully this works. Actually, perhaps I'll change that without doing the rotation. Oh, this is same time, but different days apart. I guess the main thing I'm saying here is this is a tool you can look at to get a handle on what these shape models can do for you. And visualize better about what the visualize the rotational and orientation effects of the asteroid. And I'll just, because it's very detailed, this takes a while, but there's a nice animation of the rotation of Vesta as seen in a couple of days' time. And I can't stop that from there, but I'll go on to the next slide, let that sit in the background. How do you get these shape models? It's a download. You could try maintaining the shape models yourself, but there are some little complications. And periodically, when they update the shape models, I upload a new set of files of the shape models. I forget how many thousand are in there now, several thousand shape models. And that gives you access to this capability, which, amongst other things, it's good to be able to match what other people think the shape of the asteroid is to what we get with our occultations. And I will call it quits there. And yeah, take questions.
Any questions for Dave Herald?
Is it boring as hell or stunned mullets?
Well, Dave, I want to thank you for a great presentation. It's always interesting to see those shape models move, and they're so useful for fitting to a multiple chord observation, you know, to kind of get a handle on the chords and so on. I have a hunch we're going to be using them more and more in the future.
Yep.